Okay, so what we got in question 642 is we've got this guy and he's standing on a cliff. There he is. And down below there's some water. And what he does is up here, he grabs hold of a vine and he swings his way down to the water. And then he lets go and goes plop. And we know, we're told that at the instant that he goes plop, he is travelling at 13 metres per second. So speed here is, I'll call that V1 is equal to 13 metres per second. And initially, he's up, standing on this cliff, which is a height h. And we're not told that, but I'll just give it a name anyway. Then what he does is, because that was such great fun, he climbs back up the cliff and does it again. Only this time, instead of letting go down there, what he does instead is he swings on his vine down to here, but then he keeps swinging back up until he's at a height that I'll call h2. And his speed here is what I'll call V2, and we don't know what that is. That's what the question wants us to figure out. Now, the height of the cliff will presumably be the same as what it was in the first case. But here we're also told what h2 is. h2, the point at which he lets go the second time round, is 5.2 metres. And from this information, they want us to figure out what the speed of this guy is here when he lets go at this point. So if we were just going to do that over here, what we could say, I guess, is that because the vine, so in fact, I think there are a couple of forces which are acting on this guy. One is gravity, obviously, that's an obvious one. There's also air resistance, but we're told to ignore that. The other force acting on this guy is the force that the vine applies to him. However, if you imagine the vine, it's going sort of swinging around like this, and at all points, that force that the vine is applying to him is acting perpendicular to the path that he's tracing out. And so in this case, that vine can't do any work because the force that it applies to him is always perpendicular to this guy's motion. So the only force that we're going to look at that's doing work on him is gravity. So we can say since force applied to person by the vine, sorry, a rope, he's not actually Tarzan, it's just a rope he's got. By the rope, since the force applied to the person is perpendicular to his motion, it does no work on him. And so in that case, the net work on him is just equal to the work done by gravity. So this is work done on person by gravity. On him, I should add. And so this is the network on person. Now, the work done on him by gravity, we know, is going to be equal to the negative of the change in his gravitational potential energy. And since that is the net work, we also know that that has to be equal to the change in his kinetic energy by the work kinetic energy theorem. So we can figure out the change in this guy's kinetic energy by calculating the change in his gravitational potential energy. So here, so we can say that hence, minus the person's final gravitational potential energy, minus his initial gravitational potential energy, is going to be equal to the change in his kinetic energy. So this is really just a half mv2 squared. So where the mass of the person is m. So I don't actually know that, but that's what his kinetic energy is. If we did know what his mass is, it would be equal to his final velocity squared, and then of course minus 0, because his initial kinetic energy was just 0 because he starts from rest. His final kinetic energy is just equal to his mass times the square of his final speed times a half. Now his final gravitational potential energy then is just his gravitational potential energy here, which is going to be, if we define 0 meters here, so this will be the reference point, so the reference level, in that case, his final gravitational potential energy is going to be equal to his mass times g times this height. His initial gravitational potential energy is going to be his mass times g times this height. And that's going to be equal to his final kinetic energy. Now here, one of the things I see is that all the factors have a factor of m. So we can cancel all these m's out. And what we're then left with is minus g. That's going to be h2 minus h. So what I've done there is I've factored out a g as well, cancelled the m's, and then factored out a g. And that's going to be equal to a half v2 squared. Now let's multiply both sides by half to get rid of that annoying factor of a half there. And so we'll find that that's equal to 2g h minus h2 has got to be equal to v2 squared. And so finally, if we take the square root of both sides, we find that the velocity of the guy when he lets go up here is going to be equal to the square root of 2g h minus h2. And that cancellation of the mass was particularly good because I don't know what the mass of this guy is. Now I do know what g is, that's obviously 9.8, and I do know what this h2 is, it's 5.2. Unfortunately, I do not know what this height here, I don't know what the height of the cliff was. However, there's one other piece of information that I haven't yet used, and that is that the speed of the guy when he just went straight down and let go here was 13 meters per second. So it's possible then that we could use this bit of information here to figure out the height. So let's see if we could do that. Well, again, because the force applied by the rope is perpendicular to motion, there's no work. So since, I guess we better write it out again. By rope is perpendicular to motion, it does no work on him. In that case, so the net work done on person is just that done by gravity. And so here we know that the net work done on the person is going to be equal to the work done by gravity is equal to the minus the change in his gravitational potential energy. And so since the network is, by the work kinetic energy theorem, equal to the change in his kinetic energy, that's just equal to change in kinetic energy. And if we now write down what the change in this gravitational potential energy is, we find that his final gravitational potential energy, well, if this is the reference level, then since he let go at the reference level, that means that his final gravitational potential energy is just going to be 0. So it's going to be 0 minus his mass times g times the height. So this is his initial gravitational potential energy. And then that's got to be equal to a half m times his mass times v1 squared minus 0, because his initial kinetic energy was just 0. And luckily, once again, we find that his mass cancels out because it appears on both sides as a common factor. And here we can do a bit of simplification because we have a minus times a minus. So we have g times h is equal to a half v1 squared. And so if we multiply both sides of this equation by 2, then we find that v1 squared will be equal to 2gh, and taking the square root of both sides, we eventually get to that his final speed was just equal to the square root of 2g times the height that he jumped off at. From which he jumped off. And this is pretty handy. So I think, no, you know what? I've solved for just the wrong thing. Sorry about that. So that's true. But I'm not particularly interested in this because I already know that. Well, it's not wrong, it's just not very useful. So let's just cancel that out and solve for h instead, which is what I really want. So h is going to be v1 squared divided by 2g. And let's call this equation 1. And so if we go back over to here, we can then say plug in h from 1. And what we find is that the guy's final speed when he lets go there is going to be equal to the square root of 2g v1 squared divided by 2g minus h2. And if we expand out these brackets, what we then find is this is going to be the square root of v1 squared, because 2g divided by 2g just gives us 1, minus 2g times h2. And so if we plug some numbers into this, we then get that the answer must be v1 squared, which is 13, minus 2 times 9.8 times by 5.2. And I get 8.19 meters per second.